So it continues. Clebsch Gordan coefficients are the expansion coefficients. Just now see, this is your expansion coefficients of total angular momentum eigenstates in an uncoupled tensor product basis. They arise when we couple two angular momenta, either orbital angular momentum or spin angular momentum. Okay, this is uncoupled. Okay, uncoupled tensor. So we are going to couple these one. So they are all individual states, uncoupled one tensor product that will give you coupled basis. And of course, this will be antiparallel. This will be parallel with the two magnetic moments which we discussed earlier. And this is another selection rule: m equals m1 plus m2. So the addition of angular momentum with two parts of a system is associated with the orbital angular momentum of two electrons, L plus S. Okay, the calculation of finding total angular momentum is difficult. Hence, vector auto model is used. So vector auto model is nothing but your space quantization, where J becomes constant. J is constant. M alone will vary. The projection vector alone will vary. Okay. So your J is Z, which is equal to your M is Z H bar. That alone will vary. To solve the problem with the help of addition of angular momentum, J1 plus J2. The magnitude of the same angular momentum can have angular momentum values ranging from the sum of magnitude, parallel and antiparallel. The vector auto model also states that the sum of the Z components. So sum of the Z components of the angular momenta equals to their resultant. So this is essentially for understanding the submolecules in any system. Of course, we'll have collection of electrons will be there. So we'll have to need only the total angular momentum of all the electrons. So we need to study the total angular momentum, no other way. Okay. So J1 plus J1Z plus J2Z will give you M1 plus M2. And these things we know already. Okay. So we know already the eigenvalues of equations of J1 square and J1Z, J2 square, J2Z, we know already. The eigenvalues are given by this expression. And the limitation will be where M1 goes from minus J12 plus J1, M2 goes from minus J2 plus J2. So we know already this. And also we know this one, they are commuting variables. They will have simultaneous common eigenstates. We know already. Okay, J1, J2 equal to 0, J1 squared J2 is equal to 0. Okay, they are all orthonormal eigenstates. And of course, the dimension will be 2J1 plus 1 with a tensor product of 2J2 plus 1. Okay, so we are going to transform this basis to that basis. Okay, uncoupled basis into new basis, and we are going to have Clebsch Gordan coefficients. Okay. So the unknown cuts J, M can be written as a linear combination of this. So how to write this one? So this is a coupled basis. This will be your uncoupled basis. They are all orthonormal sets. We can expand. So we just expand this one. So you have C1 plus C2 plus C3. They are all orthonormal basis states. Suppose if I take bra on this, okay, this is ket psi, okay, bra, I am going to take bra on both sides. I will have only C1 component. I will have 0 here, I will have 0 here. Is it okay? I am going to take the bra vector of this one, that will give me C1 alone. So this will become 1. Okay, taking bra of this, answer will be 1. Taking bra of this, answer will be 0. Taking bra of this, answer will be 0. Everywhere it will be 0 because they are all orthogonal. This alone will be normalized. So the answer we can get as C1. Suppose we are going to take the bra on everywhere. Bra of this one or everywhere. And you will get C2 alone. C1 will be 0. C3 will be 0. So that's why I said they are all orthonormal sets, complete sets. Okay, so they are all orthonormal bases. The coefficients of linear combinations are Clebsch Gordan coefficients. So those coefficients which we are going to get out of the projection vectors, those coefficients nothing but Clebsch Gordan coefficients. Okay, so they are all Clebsch Gordan coefficients. These coefficients in terms of matrix form are given by multiplying equation 5.87 by bra J1, J2, M1, M2. So how to get the Clebsch Gordan coefficient? Just you have this equation earlier. We studied 5.87 and 5.87. You just multiply bra J1, J2, M1, M2 here. So we will have this equation 5.88. And what is the answer for this one? This answer will be 1. So you can get the Clebsch Gordan coefficient, which is nothing but the projection vector coefficients which is nothing but your C, J, M, M1, M2 is given by this expression. So we have transformed from uncoupled to coupled. Okay, so they are all orthogonal bases and they form a unitary matrix. As I said, this one we are going to have in a matrix form. This will be a unitary matrix, which we will see later. Okay, this will have a unitary matrix. So the transformation from uncoupled to coupled will be unitary transformation. So as we have already stated earlier for the pictures, from one picture to another picture, we will have to go only with the unitary transformation. So substituting 5.89 and in 5.88. Okay, you just substitute 5.89 in 5.88. We will have this. Okay, we will have this expression. And what is this value? This is a number. Correct. So normalization constant. Of course, this is the inner product. This is a number. I can pull this number out this side. So this, let it be here. I can pull this one out here, and this is called your Clebsch Gordan coefficients in a matrix form. So this will be your uncoupled basis. This will be your coupled basis. Okay. Of course, these two is nothing but your identity operator I. Okay. So projection operator projects any vector onto the subspace. We know already. So using the transformation matrix, the uncoupled matrix can be converted into coupled matrix. The inverse of this one, 5.91 is given by this expression, inverse of this. So you can have some inversion, correct? This will be your inversion. So that is given by this expression. So what we call this as inverse form of Clebsch Gordan coefficients. Okay. So inverse of this, just to bring this term here, you will get this inverse of this. So your J1, J2, M1, M2 is given by this total expression. So this is inverse Clebsch Gordan coefficient. See here. Again, your M goes from minus J to plus J. So which is your parallel and anti-parallel. So this will be your parallel and this will be your anti-parallel. Now we have already discussed two selection rules. One is M equals M1 plus M2. The another selection rule is, come on, your J max J lies between minus J and plus J, correct? And minus J will go from modulus of J1 minus J2 plus J, that will be J1 plus J2 with the modulus, correct? We are going to see these two selection rules. So now M max is given by M1 max plus M2 max. We know already. So your M max will be, we are having two angular momentum. So M1 and M2. So M max will give you M1 max plus M2 max. And of course M1 goes from minus J1 to plus J1. M2 goes from minus J to plus J2. Okay. Your J1 is a maximum value here. And J2 will be the maximum value. So maximum value for the first one will be J1. Maximum value for the second one will be J2. So your M max will be J1 plus J2, which we denote as J max. So J max equals J1 plus J2 mod. Can you remember? This is the first selection rule. Similarly, J minimum. So that will give you J1 minus J2 if J1 is greater. J2 minus J1 if J2 is greater. It can be either one, it can be greater. Okay. So your J will lie between your J has a value anti-parallel to parallel. Anti-parallel to parallel. Okay. So mod of J1 minus J2 that will give you mod of J1 plus J2. And you go, M goes from minus J to plus A. So this is one selection rule. Okay. J lies between these two values. This is one selection rule. Okay. Now we will go for the another selection rule. Another selection rule is nothing but M equals M1 plus M2. So we know that the component of total angular momentum Jz is given by J1Z plus J2Z. We know already. And this equation also we know Jz acts on Jm. Okay, Jz sandwiched between this one. Jm is given by this expression. So J1Z can be replaced by J1Z 1 plus J2Z. See, Jz can be written as J1Z plus J2Z. Jz acts on J, M will give you M H cross J, M. We know already this. Okay, now we will take the first one. Okay, so the answer will be First we will take this one. Jz acts on Jm will give you M H cross Jm. So M H cross this value. Is it okay? Equals J1Z acts on Jm. J1Z acts on Jm plus J2Z acts on Jm. So I have written individually. Is it okay? J1 is here, J2Z is here. Now J1Z acts on Jm will give you M1 H bar. J2Z acts on Jm will give you M2 H bar. Is it okay? Very simple one. This one acts on Jm will give you M1 H bar. J2Z acts on Jm will give you M2 H bar. I have pulled out. H bar will cancel. Your M H bar will give you, which is equal to this one, M1 plus M2 H bar will cancel. You bring this term here, this side. So you have common terms. Take the common terms. M minus M1 minus M2 will be this one. And of course, this is your Clebsch Gordan coefficients. That cannot, this is equal to 0. This cannot be equal to 0. Only possibility is this can be equal to 0. If Clebsch Gordan coefficient is 0, then there will be no answer at all. So it will not be 0. So you have M minus M1 minus M2 equal to 0. It implies that M equals M1 plus M2. So this is another selection. Okay. Now we will go for one simple problem. How to find the Clebsch Gordan coefficients for J1 equal to 1 and J2 equal to 1 by 2. Okay. So for the problem is J1 equal to 1, J2 equal to 1 by 2. Okay, we will see. So J1 equal to 1, J2 equal to 1 by 2. For J1 equal to 1, your M1 will be minus J2 plus J. So you will have 1, 0, minus 1. Come on, listen to me. Very simple one. M1 will be 1, 0, minus 1. And if J2 equal to 1 by 2, your M2 will be minus J2 plus J. So 1 by 2 minus 1 by 2. Okay. This is for the uncoupled one. And the basis will be J1, J2, M1, M2. Get J1, J2, M1, M2. Now we will go for the coupled one. Coupled one, the basis will be J, M. So this is for the uncoupled one, this is for the coupled one, J, M. And J goes from J max to J minimum. So J1 minus J2 to J1 plus J2. J1 minus J2, what is the answer? J1 minus J2, your J1 equal to 1, J2 equal to 1 by 2. What will the answer? J1 minus J2? 1 by 2. So 1 by 2. For corresponding A will be 1 by 2 minus 1 by 2. Okay. Is it clear? And for J1 plus J2, the answer will be 1 plus 3 by 1 by 2. So answer will be 3 by 2. Corresponding M will be minus J2 plus J. So 3 by 2, 1 by 2, minus 1 by 2, minus 1 by 2. So this is for the coupled one. What are the dimension? Dimension for 2J plus 1. So 2, 3 by 2 plus 1, that will be 4. 2, 1 by 2 plus 1, that will be 2. So 4 plus 2, 6 bases will be there. If it is so for coupled, there must be same basis for the uncoupled one. We have already discussed. Correct? What are the basis for uncoupled? The same basis also will be for coupled one. Same basis will be there. So again, there will be 6 basis for the uncoupled one. 6 basis for the coupled basis. Is it okay? Now we know that this expression from Clebsch Gordan coefficients. Okay, J, M is given by this expression we know already. What is this one? This is your Clebsch Gordan coefficient, which we are going to find out for J1 equal to 1, J2 equal to 1 by 2. Okay. Now we will stop here. We will first represent in terms of this table first. So this is for the coupled one. Sorry, uncoupled one. This is for the coupled one. See here, uncoupled one, J1, J2, M1, M2, and this is for JM, coupled one. First we will go for coupled one. Coupled one, J, M. You just see here, J, M. So you will have 3 by 2, 3 by 2, 3 by 2, 1 by 2, 3 by 2, minus 1 by 2, 3 by 2, minus 3 by 2. So 4 are there. Remaining 2 will be 1 by 2, 1 by 2, 1 by 2, minus 1 by 2. 4 plus 2, 6. 6 are here. Very simple. Is it okay? Is it okay? This one. Then we will go for uncoupled one. J1, J2, M1, M2. As I said earlier, J1, J2 will remain constant throughout. See, 1, 1 by 2, 1, 1 by 2, 1, 1 by 2, 1, 1 by 2. See, throughout. What is changing? M1 and M2 alone changing. because this is spherical harmonics. Direction alone will change. We'll give the projection vector. So it's very clear. Now we'll go for M1 and M2. M1 and M2. So you will have 1 1 by 2, 1 minus 1 by 2. See here? Is it there? 1 1 by 2, 1 minus 1 by 2. 0 1 by 2, 0 minus 1 by 2, minus 1 1 by 2, minus 1 minus 1 by 2. See? Minus 1 minus 1 by 2. Simple one. So again we have 6 bases for the uncoupled, 6 bases for the coupled. Is it okay? Now we are going to calculate. We are going to calculate C1, C2, C3, C4, C5 and C6. So there will be 6 bases. So 6 components will exist. 6 Clebsch Gordan coefficients we are going to find out. The first one, we will calculate the first one. So 3 by 2, 3 by 2. So which is equal to C1, 1, 1 by 2, 1, 1 by 2. Is it okay? Very simple one. The first one. So you are 3 by 2, 3 by 2, which you are going to find out. Now C1 we are going to find out. C1, 1, 1 by 2, 1, 1 by 2. Okay. Just take the bra of this vector. Bra of this vector. Just take bra of this vector. Answer will be 1. Bra of this vector answer will be 1. You will have to multiply with the complex conjugate. Correct? C1 star multiplied by C1. So that will give you C1 squared mod C1 squared. Is it okay? C1 star multiplied by C1. So that will give you C1 mod square. Answer will be C1. Your C1 will be, now we said C1 mod square. We should not have any minus value. Real numbers. Clebsch Gordan will be real numbers we said. So C1 will be 1 and C1 should be positive value. So we have found out now C1. Which answer is it? Answer is 1. Positive value. Is it okay? Simple one. So we have calculated the first Clebsch Gordan coefficient C1. Now we will go for the next one. Next one is 3 by 2, 1 by 2. So next one is 3 by 2, 1 by 2. So 3 by 2, 1 by 2. So now to have 1 by 2, come on, listen to me. To have 1 by 2, we can have two possibilities. 1 minus 1 by 2 or 0 plus 1 by 2. This is your M. This will be your M1 and that will be your M2. So this will be your M1, that will be your M2. This will be your M. What is selection rule? M equals M1 plus M2. To have M1 as 1 by 2, we can have two possibilities. Either we can go for this or either we can go for this. 1 minus 1 by 2 will give you 1 by 2. 1 minus 1 by 2 will give you 1 by 2. 0 plus 1 by 2 will give you 1 by 2. See, we have 1 by 2. Is it clear? So we have linear combination of these two bases that will give you complete set. So this will be your uncoupled, this will be your coupled one. We have used the selection rule. Not clear? So I repeat. See here. To have 1 by 2, we must have M1 plus M2. So this is your M1 plus M2. So either we can have 1 minus 1 by 2 or we can have 0 plus 1 by 2. Both will get the result as 1 by 2. Using the selection rule. Okay. Now you just see here, we have already calculated C1. 3 by 2, 3 by 2. Now I am going to use raising and lowering operator for this one to get this value. So this is your 3 by 2, 3 by 2. Correct? This is your Jm. I am going to use raising or lowering operator. Suppose if I use a lowering operator, 3 by 2 for this. If I use lowering operator, J minus. So lowering operator means M becomes M minus 1. Lowering operator. For raising operator, M becomes M plus 1. So lowering operator, M becomes M minus 1. So 3 by 2 minus 1 will give me 3 by 2 minus 1 will give me 1 by 2 minus 1. Answer will be 1 by 2. See, 1 by 2. I repeat. See, this is your M. I am going to use lowering operator. So M becomes M minus 1. Correct? So M is 3 by 2. 3 by 2 minus 1 becomes 1 by 2. So to achieve this one, I will have to use lowering operator. Very simple idea. So lowering operator operates on 3 by 2, 3 by 2. will give me j minus complete one, okay, coupled one, that will give me j1 plus j2 minus. This is for uncoupled one, correct? And what are these bases? These bases will be the same basis. See here, these bases will be the same basis. Is it okay? So j1 is the eigenvector of this one. j1 minus plus j2 minus the eigenvector of this one. Okay, this will be the eigenvector. Now we know already the eigenvalue of lowering operator is given by this formula. We know already. We studied in the last video class. Okay, and your m goes m minus 1. It's very important one. Eigenvalue equation of a lowering operator j comma m will give you this value with the ket j comma m minus 1. See, look at this, m becomes m minus 1. Now we'll go for first left hand side. Left hand side is this one. Okay, so your j will be 3 by 2, m will be 3 by 2. Your j will be 3 by 2, m will be 3 by 2. So 3 by 2 plus 3 by 2. J will be 3 by 2 minus m will be 3 by 2 plus 1, and this will cancel. Correct? This will get cancel. You will get 3 by 2 plus 3 by 2. So 2 3 by 2. 2 will get cancel. You will have 3 under root. So this will be root 3. The answer, this will be your root 3. Is it okay? So left hand side we have calculated as root 3 h bar. Come on. Root 3 h bar. Very simple one. Now we will go for the right hand side. Right hand side first term. We will go for the first term. This will be your second term. So right hand side first term. So write the same equation. Okay, same equation, and j1 acts on j1, j2, m1, m2 will give you this one. And you know, very important thing is j1 acts on only m1, not on m2. See, this m1 will change into m minus 1. Very important one. Is it okay? See, earlier 1 by 2. See here, 1 by 2, 1 by 2. Okay, here this is m1, this is your m2. j1 will act only on m1, not on m2. So this will become minus 1, m minus 1. 1 minus 1, answer will be 0. See here, 0. Rest of the things let it be like this. And you are going to use j1, j2, m1, m2. So that will give you 1 plus 1. This one will cancel. You will have root. Okay. So this will cancel. You have 1 multiplied by 2. That will give you 2 under root. So root 2 h bar. Now we will go for the right hand side, second term. Is it okay? Now j2 minus will act only on m2, not on m1. So this will become only m2 minus 1, not on m1 minus 1. m1 it will be as it is, m2 minus 1. Okay. So what about m2 minus 1? We know already this is 1 by 2. 1 by 2 minus 1? Minus 1 by 2. See, minus 1 by 2. All the other terms are, they are like this. Is it okay? How to write this? Okay. See here we have 1 by 2. This j2 will act only on 1 by 2. So m becomes m minus 1. So answer will be minus 1 by 2. Is it okay? So your j2, the eigenvalue will be 1 by 2 plus 1 by 2. This will cancel. You will have 1 by 2, 1 by 2. Answer is 1. So root 1. So 1 h bar. So now this will be your complete expression. This will be your complete expression. So we have calculated root 3. Can you remember? So for the coupled one, so root 3, ket 3 by 2, 1 by 2. This will be this term. So root 2, and this will be your root 1. So 1. So this is the answer. Okay, this is the final answer. Now you will have to divide throughout by root 3. So bring root 3 down this side. So you will have this term. What is this one? Can you remember? Root 2, this one will be your C2 and this will be your C3. So this will be your C3 and this will be your C2. You compare these two. That is the equation which we had earlier. So C2 and C3. I have interchanged. See here, 1 by 2, 0, 1 by 2, 1 by 2, 0, 1 by 2. That will be your C3 and this will be your C2. So C2 is given by this 1 by root 3. C3 is given by root of 2 by 3. Now take the normalization. You just take the normalization. Okay, normalization will give you C2, C2 star plus C3, C3 star equal to 1. Just you are going to take the normalization. How to take the normalization? Okay, so here you are going to take the normalization. I'll give you a small trick, it's very simple one. You are going to take the normalization. So take the bra on both sides. Okay, bra on both sides. So when you are going to take the bra on both sides, the answer will be 1 here. Here, this multiplied by this, okay, this multiplied by this one, this multiplied by this one, and this multiplied by this one. So we'll have 4 terms. We are going to take the normalize. Okay, so for that we are going to take the bra on both sides. When you are going to take the bra on both sides, we will have to assume this of its own, this of its own, this multiplied by this multiplied by this. If you multiply these two, that will give you orthogonal will be answer will be 0. If you multiply of its own, that will give you answer as 1. If you multiply of its own, that answer will be 1. So that's why we have arrived as C2, C2 star plus C3, C3 star, which is equal to 1. So what is the value of C2? 1 by root 3. So 1 by root 3 multiplied by 1 by root 3, that will give you 1 by 3 plus 2 by 3, answer will be 1. Okay. So normalization condition also is over. Everything is okay. So we have found out now C2 and C3. So earlier we have found out C1 as 1. So now C2 and C3. Okay. Still 3 more left. So now the next possibility is 1. Next one is 1 by 2, 1 by 2. What are the possibilities for 1 by 2? It can be either 1 minus 1 by 2 or it can be either 0 plus 1 by 2. Is it okay? So there are 2 possibilities. To get 1 by 2, we can have 1 minus 1 by 2 or 0 plus 1 by 2 using selection rule m equals m1 plus m2. So we know already this earlier. For C2, C3, we know already this earlier. Correct? So see, we know already second term. Now just go for the orthogonality condition. Okay, orthogonality condition. You just multiply these two. Okay, orthogonality condition. Take the bra and multiply this, or take the bra and multiply this. That's all. You will get. So different states are there. You will get 0. Correct? You have to multiply these two. I said take the bra on both sides. Correct? Take the bra and multiply. Take the bra and multiply. If you multiply these two, answer will be. If you multiply, the answer will be 1. Both are equal. Answer will be 1. If you multiply, the answer will be 1. If you multiply these two, answer will be 0. If you multiply these two, answer will be 0. Is it okay? How to do? So you will get multiply these two, that will give you using orthogonality condition, that will be 0. So C2, C4 star plus C3, C5 star. We have already we know the value. C2 we know already value. Correct? We have already calculated. C2 equals 1 by root 3, C3 equals root 2 by 3. You substitute here, which is equal to J. So it implies that C4 equals minus root 2. So multiply throughout by root 3. So that will give you C4 equals minus root 2 C5. Squaring on both sides, that will give C4 squared equals 2 C5 squared. Is it okay? Is it very simple one? Okay, now you have squared. So now applying the normalization condition for C4 and C5. You just apply the normalization condition for this or this. This alone or this one. So we will have this one alone. Okay, applying the normalization condition for C4 and C5. So we are going to have normalization condition. The answer will be 1. Here normalization condition will be, if you are going to multiply this with this, answer will be 1. This answer will be 1. If you multiply these two, answer will be 0. So we will have C4 squared plus C5 squared, which is equal to 1. Is it okay? 1. So C4 squared equal to 2C5 squared. C4 squared equals 2C5 squared. So if you add these two, that will give you 3C5 squared, which is equal to 1. So C5 equals 1 by root 3. If C5 equals 1 by root 3, you substitute here, so you will get C4. You substitute here. C5 equals 1 by root 3. 1 by root 3. Therefore, C4 equals minus root 2 by 3. So we have calculated C1, C2, C3, C4, C5. So 1 is left out. Is it okay? 1 is left out. Okay. So now putting everything in a table. J1 equals 1, J2 equals 1 by 2, So these are the conditions. Your M1, M2 will be this one. Your Jm will be this one. So earlier we got, can you remember, C1 equals 1. So this will C2, C3, C4, C5. So assignment for remaining things. You just go for remaining things. The final answer you will get 1. Okay. If you operate these two, your final answer will be 1. Can you remember? The C1 is 1. So we have used only lowering operator. You just check whether you can use lowering operator, rising operator. Just check. Okay. Either you have to use lowering operator, rising operator. You just check and do. You can get the answer. Is it okay? Now, as I said, so this can be written in terms of matrix. Clebsch Gordan coefficients can be written in terms of matrices. So we have all uncoupled states. We have all coupled states, and we are going to have Clebsch Gordan coefficients in a matrix form. So they are all Clebsch Gordan coefficient in a matrix form. Okay. See here, 1 0 0 0 0 0. See, 1 0 0 0 0. Similarly, 1 0 0 0 0 here. And this will be your diagonal elements here, 1 by 3 root 2 by 3, 0 0 remaining terms. And this will be your minus root 2 by 3, 1 by 3. Okay, C1, C2, C3, C4, C5, which we have already calculated. And again, this will be the rest of the term. And this will be the rest of the term. And at the end, you will have 1. So this is your matrix form. Clebsch Gordan coefficient as matrix elements. Okay. So they are all unitary matrix. So your capital Psi equals Ci Psi I. Of course, we know already this one. And in terms of Clebsch Gordan coefficients, we have written uncoupled to coupled with through Clebsch Gordan coefficients. Okay, so this is the expression. So by the help of matrix, we can transform from uncoupled to coupled states by the matrix equation. Okay, so that is the end. Okay, thank you students. We will see in the next class.